Hello students, let's begin lesson 7, quadratic functions and models. What is a quadratic function? A quadratic function is a function given like this, ax squared plus bx plus c form, where the leading coefficient a is non-zero. Now what if a is equal to 0? Then 0 times something is 0, so this is 0. So the entire highlighted part just drops out. And what's left is just bx plus c, and that's a linear function, not quadratic. Therefore, a should not be equal to 0. In other words, a is either positive or negative. Let's look at these two graphs. The first graph exemplifies the case where a is positive. Graph is concave up, bent upward, and we have the minimum forming here. The second graph exemplifies the case a is negative. The graph is concave down, bent downward, and we have the maximum forming there. But then again, otherwise, it's really hard to see anything here. Where exactly is the maximum or minimum? It's hard to tell because the general form is just too simple and it does not reveal a lot of information. We need some better tools. One such tool is the vertex form, which I'm going to emphasize here in section 1. f of x is equal to a times, parenthesis open, x minus h, parenthesis close, that quantity squared plus k. In this form, you can explicitly find out the vertex of the parabola as h comma k. Why h comma k? I'll explain that in a moment. Let's look at examples first. First example, when a is positive, we have a graph that's concave up, bent upward. And clearly we have minimum right here at the vertex, and the vertex is h comma k. Why is it h comma k? I'll explain that in a moment. Let's just accept it as is for now, h comma k, and in this case -1 comma -1/4, by the way. So if this is h comma k, then the minimum is y-coordinate value y equals k, and we attain the minimum at x equals to h. That's because this point is h comma k. And also, range is k to infinity, and that's easy to see, you see. And you see all these graphs going up. So y-coordinate is going up to positive infinity. No problem about that, you see. Graph is going up to the left or to the right. But down below, no, it stops at y equals to k. So we have bracket k. Now, it has to be bracket because this point, the vertex point, is part of the graph. So y equals to k is certainly allowed. When x is h, y is k. So yes, that's the minimum. Toward infinity, that's always parenthesis because nothing is actually equal to infinity. And finally, symmetric about x equals to h. Draw a vertical line here, and we have the symmetry. Left and right are the same. It's easy to see. Now, all boils down to one observation here. In this vertex form, we have this h and k, and is this h comma k really h comma k right here, the vertex? That is the question. We're going to answer that question twice. Once I'm going to answer now, and that's going to be a little bit harder. And the second time, when we deal with graph transformation, that's going to be a little bit easier. So a little bit harder way first. Okay, ready? Let's make this observation. When x is humongously positive or humongously negative, x minus h squared, that's always humongously positive, because we took square. And then a, that's also positive. So a times the square is always positive. Do you see that? As I move to the right or to the left, humongously positive. Either way. So we have this going up as we move to the right, and also here going up as we move to the left. And this whole thing is positive. So this thing is greater than or equal to 0 plus k, because this square is greater than or equal to 0. You see? square is always positive, so greater than 0. And at worst, it is equal to 0, and that takes place when the inside is 0. When is it 0? X minus h is 0, which means x is equal to h. That's when we have 0. Does it make sense? This thing is equal to 0, so we have equality, otherwise greater than k, but we have equality when x is equal to h. And when x is equal to h, we have equality y equals to k. So that's the minimum, otherwise greater than k. So when x is equal to h, right here, y is k, otherwise greater than k, otherwise greater than k. So a little bit harder way to see this h comma k is really the vertex here is coming through this inequality here. Now what if a is negative? Here's a graph. Graph is concave down, and then maximum here, this point is h comma k, so maximum point is y equals to k when x is h, alright, and the range, negative infinity going down forever, but reaching only up to k. That's also easy. Symmetric about the vertical line, x equals to h, the vertical line that's running through the vertex. Again, that's easy to see. And all this is assuming that this h comma k here, the vertex, is indeed h comma k that comes from the vertex form. Now, is that really true? Let's check it out. Now, when x minus h is, when x is humongously positive or humongously negative, that is to the right or to the left, x minus h quantity squared is always humongously positive. But then again, a is negative, so if you multiply this entire quantity, this one is humongously negative. So less than 0. So less than 0. So this quantity, a times x minus h, that quantity squared, is less than 0 in general. So we have this concave down. Going down, and we have the maximum there. Now, when do we actually reach the maximum? This one is always negative, but at best it is 0 when the inside is 0. X minus h is 0, which means when x is equal to h, we have 0. So we have equality. F of x is equal to k. That's the maximum. Otherwise, strictly less. And that's a little bit harder way to answer why this h comma k in this vertex form is indeed h comma k here in this vertex equation. We went through positive case and negative case, but in the end we answered everything. Now, I said that was a little bit harder way to understand. If you understand, good. If you didn't, let's go to the next topic here, graph transformation. Now, it's going to be a little bit easier this way. Okay. You can consider this sequence of graph transformations. When a is positive, when a is negative down here. Positive case first. Let's begin from the standard power function y equals to x squared. We already studied it. It's among those power functions, and we studied the library of functions already. Looks like this. And then let's stretch it vertically by factor of a. In this particular case, I stretched it by factor of 1.5. Basically, take all the points here in the blue graph and then multiply 1.5, or in general, multiply a to each y coordinate to get the red graph. So the graph transformation is the inverse operation. We have to divide. So we start from y equals to x squared and y divided by h, replacing y by y over a, we get this. But then again, y over a is equal to x squared. That's equivalent to just y equals a times x squared. That's what this graph is. Let's see. It's like this. Y equals x squared. And then from there, replace y by y over a. That's the graph transformation. And then from here, flipping a to the other side, you're going to get this. Alright, the shape of the graph is now all set. Now let's move it around. Let's move this graph to the right, horizontally, by h units. So I'm adding h to each x coordinate. Again, the idea is inverse operation. So I replace x by x minus h. So we get this. So move to the right. And then I move vertically by k units. So from here, y equals a, x minus h squared. From here, replace y by y minus k. That's the vertical shifting. Inverse operation, I'm adding k to each y coordinate from this green graph. Here, in this particular case, k is negative 1.75 or something, so it moves down. So inverse operation, we did y minus k equal to that. But of course, I can flip this minus k to the other side, and that's what this graph is. So if you look at it in terms of a sequence of graph transformation, vertex 0, 0 is moving to eventually h, 0 and h, k. That's easy to understand. Of course, if you understand all the details about graph transformation at each step. If you do, then that's easy. Compared with that algebraic way with inequality, this one's easier. If you understand the graph transformation. Now, what if a is negative? Same idea, actually. Originally, we have the power function. And then let's stretch it vertically. But a is negative, so when we stretch, also we have to flip it vertically because a is negative. So changing to negative, so we are flipping, vertical flipping, or flipping with respect to the horizontal axis, the x-axis. Now this is a shape. All right, let's move it around. Horizontal shifting by h units, and then vertical shifting by k units. That's it. So from 0, 0, the vertex, still at 0, 0, and then h, 0 and h, k. That's how it's moving. We took the flipping, so minimum became maximum when a is negative. Previously, when a was positive, we didn't do any flipping, so minimum stays at minimum. Otherwise, the same idea. Okay, so y, h, k is the vertex. I think everybody understands it now. And looks like we can go over to a problem. Don't have enough time for any more than one problem, so let's do this one. And this is really easy because this is already given in terms of the vertex form. So here we go. h, k is -1, -3. And is it maximum or minimum? A is -2, so this is maximum. And that's it. As for the other problems, you have to convert those into the vertex form first. So it's going to be a bit more work, and we are going to do those in the next video.